Let's try to solve this problem here. So we are given with a figure, and the figure above shows a ball of mass 1 kg. So this ball here has a mass of 1 kg, and it compresses the spring by 10 cm at position A. So this ball here is at position A, and the spring right now has been compressed by 10 cm. So let's write that down. So we have our ball. This ball here is 1 kg, and this ball is this spring here is now being compressed from its original length by 0.100 meter. Okay, we just write down all the details you have in the diagram. We don't need to draw a new diagram since the diagram is given. When the spring is released, the ball moves to position B. So when you release the spring will try to push the ball, right? Then the ball will roll towards B. So you can think of it as the path is going like this. Okay, then continues to move up the slope until it stops at position C. So you continue to move up this slope over here until it stops at C. So if it says it stops at C, that means the speed over here for the ball, the speed over here should be 0 meter per second. Okay, the surface of the path ABC is frictionless. So the whole journey from A to B to C is frictionless. It's an important statement because it allows us to check whether this situation obeys the principle of conservation or of mechanical energy or not. Okay, we'll study about that later. And the spring constant is 500 Newton per meter. So the K, or the spring constant, is 500 Newton per meter. Okay, so this is a situation, a compressed spring. You place a ball there, then you let go, the spring relaxes to its original length while pushing the ball. So the ball undergoes a journey from A to B, then goes up until it stops at C. Okay, so determine the elastic potential energy of the compressed spring. This part is still relatively straightforward. What you need to do is just use the formula for elastic potential energy. So elastic potential energy is U subscript EL. So it's half kx squared. So K will be the spring constant, so that's 500 Newton per meter. The x here will be the amount of the length of compression or the length of stretching. Okay, so in this case it's a compressed spring, so it's the length of your compression, and the compression is 0.100 meter. Okay, so if you substitute everything in, your answer should be 2.5 joule. So this is the elastic potential energy possessed by this spring over here due to it being compressed by 0.100 meter. Okay, so next we look at using the principle of conservation of energy, determine the velocity of the ball at position B. So they already explicitly say you are going to use the principle of conservation of energy. So, well, let's just use it, principle of conservation of energy. Okay, so principle of conservation of energy, to be more specific in this case, is principle of conservation of mechanical energy. Why do we know the mechanical energy is conserved? Let's try to study it. So we'll try to draw three different free body diagram. The first free body diagram will be the free body diagram when the ball is positioned at position A. That's the first free body diagram. The second free body diagram will be the free body diagram of the ball during its journey leaving the spring moving towards B. That's the second free body diagram that we will draw. For the third free body diagram, we will draw the free body diagram of the ball moving up the slope. Then we'll study this free body diagram to see whether the mechanical energy is conserved or not. Well, right now they say it's using principle of conservation of energy, but is the mechanical energy conserved or not? That is the thing that you want to look at. Okay, in usual exam, you don't need to go through this whole process, but this is an explanation video, so let's try to study the question deeper to understand what do you mean by what kind of system follow principle of conservation of mechanical energy. So for position A, if you draw a free body diagram for the ball at position A, you have your axis. Then at that point, this ball here has mass, so it has weight. Then this ball here is touching the surface. therefore it has normal. And this ball here is touching a compressed spring, and once you release the spring will exert a force to push on the ball, and that force here you can think of it as the restoring force of the spring. So I'll label it as force of the spring. Okay, so this is position A. Then I'll draw another free body diagram for the ball after it leaves A while it's moving towards B. Okay, so again, I will draw the same axis, horizontal axis and a vertical axis. Again, this ball here has mass, so it has weight. Then you know that it's still touching the ground, so there will be a normal force pointing upwards. And because the ball has already left the spring, the ball is not touching the spring anymore. And since it's not touching the spring, there will be no restoring force acted by the spring on the ball. No more restoring force of the spring. Is there any contact of the ball, if anything, during its journey from A to B? Well, the ball is just touching the ground. It's no longer touching the spring, touching nothing else. So this is the free body diagram for the ball on its journey, leaving A, moving towards B. That's all. Just weight and normal. Lastly, we have our third free body diagram, which should be the free body diagram of the ball moving up slopes. Well, the slope is changing angle throughout the journey. Previously, it was quite steep, then it gets less and less steeper. But we will just draw a arbitrary angle just to get the idea of the situation. We won't be drawing it for every single angle. We just take a random, just take one angle and draw a free body diagram for the situation. Okay, again, this is just to explain why this situation here, the mechanical energy is conserved. Okay, you usually just straight away say the mechanical energy is conserved, but let me show you why is it conserved. Okay, so it's moving up the slope towards C. Okay, so we will take a incline, an axis which is slightly rotated, something like this. So this will be representing the slope over here. Then this one will be perpendicular to the slope. Okay, so we still have weight and we still have normal. I should draw my axis more properly. And I believe that's all. Since this is a frictionless inclined plane, you should expect no kinetic friction throughout the journey. So that will be the free body diagram for this case over here. Okay, so we have to understand what is the criteria in order for mechanical energy to be conserved. So if you want our mechanical energy to be conserved, we have to make sure that the total work done by non-conservative force is equal to 0. Or you can think of it as another way as only conservative force are doing work on the object. Okay, so if we look at this situation here, there are multiple forces acting on an object. Let's try to determine which are conservative, which are non-conservative. Weight is a gravitational force. We learned that gravitational force is conservative, so let's label it C. Normal force is a non-conservative force. The only conservative force that we learn in our syllabus is just gravity and restoring force of a spring. So this is again conservative. So normal force, non-conservative. Weight here is conservative. Normal force, non-conservative. Weight here is conservative. Next, we check whether the non-conservative force are doing work or not. Okay, so this is a normal, here is a non-conservative force, normal, non-conservative, normal, non-conservative. Let's check whether the non-conservative force, whether they are doing work or not. How do we check? We can look at the angle, that's one of the way. So we see this object here, it's moving. So what is the direction of the motion? Okay, for this position A over here, the motion will be in this direction. Okay, it's moving while being pushed away by the spring. So the motion will be to the left. And as you can see here, the normal force and the displacement forms a 90-degree between them. Therefore, this normal force here does no work. So work done by normal force equals to 0. And since the non-conservative force is doing no work, the forces that will be doing work are the restoring force of a spring only. The work done by gravity here will still be 0. The only force that are doing work is the restoring force of a spring. Restoring force of a spring is a conservative force. Thus, the total work done is only caused by the restoring force of a spring. So there is no work done by non-conservative force. So for this portion of the journey, since there is no work done by non-conservative force, we can see that for this portion of the journey, the mechanical energy is conserved. E is representing mechanical energy, not energy. E is conserved at this point over here. And after leaving A and moving towards B, the only force acting on it is the normal force and the weight. Again, the motion after leaving A moving towards B, the motion is again towards the left. So we know that both of these will do no work. The work done by the normal force will again be 0. The work done by the weight will also be 0. So since this case the total work done is 0, you should expect no change in kinetic energy. Thus, you should expect no change in the speed of object. Or in other words, the object will be moving at constant speed throughout the journey after leaving the spring, moving towards the position B over here. So again, since there's no work done by non-conservative force, you can say that the mechanical energy is again conserved. Okay, let's look at free body diagram, the third free body diagram. Now the object is moving up the slope, so the displacement is in this direction. Now for this case over here, again we see that the normal force and the displacement forms a 90-degree angle between them. So this non-conservative force, the normal force, still do no work on the object. So now we are left with the weight here. Is the weight going to do work? Yes, indeed. The weight here can be resolved into two components. One component is perpendicular to the direction of motion. So this component W, the Y component of weight here will not do work. Whereas the X component of the weight, which is in this direction, the X component of the weight will be doing work. But it's a negative work since the displacement and the X component of weight are in opposite direction. So you should expect negative work. So the total work done is only the work done by the X component of weight. So since the work done by X component of weight is negative work done, you can expect the total work done to be negative. And since the total work done is negative, you should expect the kinetic energy to decrease. Thus, you can observe the ball is actually slowing down as it moves up the slope. So everything still makes sense. In this case, the only non-conservative force, which is the normal force, is not doing any work. So in this case, all the work done here are done by conservative force. Thus, we can say the mechanical energy is still conserved for this situation here. And now we have proved that the whole journey from point A to point C, the mechanical energy should be conserved. This is just to explain the situation only. You don't need to do this in your exam. I'm just trying to show you why the mechanical energy is conserved for this case. It's because the work done by non-conservative force is equals to 0. Those work done, there is work done on the object, but all those work done are carried out by conservative forces only, such as the weight over here or the restoring force of a spring. Those are conservative force, and these are the conservative force that are doing work only. No non-conservative force doing work. Okay, so let's move on to the theory and try to solve this problem. Problem 2 over here, you are going to use the principle of conservation of energy. So again, the idea is picking two different positions to investigate. So the first position that we are going to investigate will be the position that we know most of the information. So that will be point A over here. We know the object is at rest. We know the spring is being compressed. So this will be the first position that we will use, because that position we have a lot of information. The second position will be the position we are interested to know something about. And that second position will be position B, which we are interested to know its velocity. So now, since we have determined the two positions that we will be using, let's do our principle of conservation of mechanical energy. So we write down that the mechanical energy at position A will be equals to the mechanical energy at position B. So the mechanical energy is the sum of kinetic energy plus the potential energy, but potential energy can be split into the gravitational potential energy and the elastic potential energy. Okay, the other side you have the kinetic energy at position B, the gravitational potential energy at position B, and the elastic potential energy at position B. Okay, now once we know that, let's bring in the formula for the kinetic energy and the potential energy. So kinetic energy will be half mv squared, but this will be the speed at position A. Okay, mgh for the gravitational potential energy, but this will be the height at position A. Next, we will take the elastic potential energy at position A. So this will be half kx A squared. The x here will be the amount of compression when the ball is at position A. Okay. Next, kb here will be half mvb squared, because this will be the speed at position B. Then you have mg hb. Then you will have half kxb squared. Okay, so once you have written down the equation here, well, you can proceed to do substitution. Then you say a lot of things are zero, so you can cancel out. But because I'm not going to write down all the substitution, I'm going to cancel out the terms that will be equal to 0 first. Okay, first we know that this ball here is being placed at this position A here while it compresses the spring by 10 cm. So at that moment, before you release the spring, the ball must be stationary. After you let go of your hand, the ball only will be pushed by a spring, then you start to move. So initially at position A, you should expect the ball to be not moving. And since the ball is not moving, you should expect the speed at position A to be 0. Thus, the kinetic energy at position A should be equal to 0. Next, you look at the height. For now, for this situation, it's most convenient to set this position as our reference position. Okay, reference position is for gravitational potential energy. So gravitational potential energy, we have to set a place where our gravitational potential energy is equal to 0. And we set it to be the ground. So we can say at the ground, our h is 0. Thus, our gravitational potential energy is 0 for the ground. If you go above the ground, your gravitational potential energy will be positive. If you go below the ground, you go underground, you go below the ground, then your gravitational potential energy will be negative. We have to set a reference position first. And since we set the ground to be our reference position, then we say that at the ground, the ball is still at the ground, so the gravitational potential energy should be 0 because the height is at the ground, the reference position. Next, we look at the spring. The spring is now being compressed by 0.100 meter. So since it's being compressed, you should expect there will be elastic potential energy. So this one we have to leave it here. Next, we look at position B. Once the ball has moved to position B, it must be having some kind of velocity. Because the ball has already left the spring, then after the ball leaves the spring, it will still continue to move. Because as I said just now, after it leaves A, moving towards B, there will be 0 total work done. Okay, when it's 0 total work done, you should expect the ball to have no change in kinetic energy. So if the ball is moving with a certain speed, it will still remain at a certain speed. Then there will be no change in kinetic energy during its journey after it leaves the spring while it is moving towards position B. Okay, so since there will be a velocity and we are interested to find the velocity, we have to leave this term here because we want to find an answer from this term over here. Next, the height at position B. Position B is still aligned with the at the same height as the reference position. So you should expect the height for B is 0. So this term here will be cancelled to 0. And next, at position B, the spring has already fully released to its original length already. It has really left the spring already. So leave the spring, there should be no compression or stretch to the spring already. Therefore, you should expect the x here to be 0. Thus, this term will also be cancelled to be 0. So now we have cancelled a lot of terms. We are left with the elastic potential energy on the left hand side and the kinetic energy on the right hand side. Well, now it's just substitution. So we are going to substitute half our spring constant 500, amount of stretch or compression, that is 0.100. Well, you can choose to put negative here actually, because you want to say compression is negative, you want to say stretch is positive. It's up to you, okay? But the thing is, there's a square here, so no matter what sign you put, you will still gain back to a positive value. And for elastic potential energy, it's always a positive, okay? Next, we have half mv square. The ball is 1 kg. Then the speed of the ball at position B is what we are interested to find. So now we are left with one unknown only, which is the speed at position B. So speed at position B, you can use your calculator to calculate. I believe the answer that you will get is VB is equals to 2.24 meter per second. So this is the speed of the ball once the ball has reached this position B. But since they ask for velocity of the ball, if you give speed, you might feel a bit insecure. Didn't include the direction. So you can include the direction. Well, yeah, you can include the direction. You say V at point B is equals to 2.24 meter per second. And it's, 2 meter per second. Then currently is still moving to the left. So you can write moving to the left. Okay, nothing too complex until now. Okay, so this is question 2. Next, we move on to question 3. Question 3 asks us to determine the maximum height h that the ball can go up and stop at C. Okay, why do we call it height, maximum height? Why don't just call it height? Let's try to discuss that further. Okay, so this hill here, right, has a height of h. If this height of h is not a very high hill, let's call this what do they call this? Let's call this a hill. Let's say the hill is not so high. Then what will happen is the ball is coming towards the hill with a certain kinetic energy, right? If the hill is not so high, a portion of the kinetic energy at position B will be transformed into potential energy when the ball reach the peak of the hill. Then there will be still some kinetic energy remaining, thus the ball will still be moving at a certain speed while going to the left at the top of the hill. That is, if the hill is not very high. But as you increase the height of the hill, then what will happen is more and more kinetic energy will be transferred or transformed into potential energy to be stored, because due to the increased height of the peak of the hill. So if you are left with less and less kinetic energy, the speed of the ball when it reaches the peak of the hill will decrease as the peak of the hill gets higher and higher. And once you reach a certain height, all of the kinetic energy at position B will be transformed into potential energy to be stored at the ball when the ball reaches the peak of the hill. And if all of the kinetic energy is being transformed to potential energy, there will be no kinetic energy left. Thus, the ball will reach or will slow down to a stop the moment it reaches the peak of the hill. And that height will be the maximum height that the hill can be if you want the ball to reach the peak of the hill. If you go higher than the height, the maximum height, if your hill is higher than this maximum height, what will happen is the ball will reach a certain height, exhausted all its kinetic energy being transformed into potential energy, but you still haven't reached the peak yet. In that case, what will happen is you are not able to reach the peak of the hill. What we'll do is you roll back down towards the valley here. Okay, there's a maximum height that you can have for this hill in order for the ball to reach the peak. If you go higher than that, what you will do is the ball will not reach the peak, it will fall back down. Okay, so let's find the maximum height. We will be using principle of conservation of mechanical energy. So again, principle of mechanical energy says that the mechanical energy at all positions during the journey should be the same. So what are the positions that we are interested in? We are interested to find something related to this maximum height. So definitely we'll be interested in position C. Okay, next position, we need to pick two positions. One position where we are interested to find something. Another position will be a position where we know most of or all of the information that we can determine for that position. For position A, you can determine all of the information. You are able to determine the kinetic potential energy. You are able to determine all of this. So position A is a good point to pick. Position B is also a good point to pick because position B, you know there will be no elastic potential energy, no gravitational potential energy. What will be left is just the kinetic energy, and you know the speed from the second question. So you can still pick position B as the position that you use for the equation. But for now, I'll be using position A, and I will say position A has the same amount of mechanical energy as position C. Okay, so what I'll write is the mechanical energy at position A is equals to the mechanical energy at position C. So that means the kinetic energy at position A plus the gravitational potential energy at position A plus the elastic potential energy at position A is equals to the kinetic energy at position C plus the gravitational potential energy at position C plus the elastic potential energy at position C. Okay, the similar steps to question 2. Now we bring in the formula for all of this energy. Kinetic energy is half mv squared. So this is the speed at position A. Gravitational potential energy is mgh. In this case, this is a height at position A. Elastic potential energy is half kx squared. In this case, x here is the amount of compression or stretch at when the ball is at position A. Next, we have kinetic energy at position C, which is half mv squared. The v here is the speed at position C, which in this case we know will be at rest later. Next will be the gravitational potential energy, mgh, height at position C. Lastly, you have your half kx squared, where this x here will be the amount of compression of the spring when the ball is at position C. Okay, so now we are going to cross out some terms. We know some of the terms here will be 0, so let's try and do that. We know the ball is at rest when it is at position A. It is compressing the spring. You haven't released the spring, so the ball remains at rest at that position. So you should expect the kinetic energy for position A to be 0. Next, you know that the ball is right now on the ground. We set our ground as our reference position, so the gravitational potential energy will still be 0. Then what's left is just the elastic potential energy, which we know will be not 0 because the spring is being compressed at position when the ball is at position A. Okay, move on to position C. For position C, you know that over here the kinetic energy should be 0. Okay, because we want the ball to stop at C. To stop at C, your kinetic energy should be 0 at C. So you can say this is 0. But the gravitational potential energy should not be 0 because you have reached a certain height above the reference position. Position C is at height h above the reference position, so therefore you have a positive gravitational potential energy. Next, for the elastic potential energy, the spring is no longer compressed when the ball is at position C. So you should expect the elastic potential energy for here to be 0 as well. So now we are left with one term for both sides. For the left hand side, you have your elastic potential energy. For your right hand side, you have your gravitational potential energy. So let's write all these things down and do our substitution. So half k x 0.100 square equals to mgh, the mass of the ball is 1 kg, acceleration due to gravity 9.81, the height is what we are interested to find. Now the only unknown left here is the height at position C, so you can key it into your calculator, and I believe you can get answer to be 0.255 meter. Okay, so this will be the maximum height for this hill over here if you want the ball to reach a stop when it reaches the peak of the hill. If your hill is higher than 0.255 meter, the ball will not be able to reach the peak of the hill. If your height of the hill is less than 0.255 meter, what will happen is the ball will still retain some speed once it reaches the peak of the hill. So it will not stop, it will continue to move with a lower speed once it reaches the peak of the hill. So this is how we use principle of conservation of mechanical energy to analyze the situation where the mechanical energy is conserved. For sure, first thing is you need to determine two positions first. One position will be the position where you know all the energies, The second position will be the position where you are interested to determine something, like the height or the speed, something like that. Okay, then you break it down into its kinetic and potential energy, find the terms relevant, find the relevant quantities like the speed, the mass, the height, bring it in, substitute, then you should be able to get your answer. Okay, so this is how you do a question like this.